Let us now have a brief look at boundary conditions in DEM-based simulations. First, we consider the simple and most obvious boundary condition of a flat wall. This is a boundary condition that one would use in a coed flow arrangement, i.e. the flow of a material between two walls with different wall velocities. Classical fluid mechanics, relying on the continuous theory, would tell us that a linear velocity profile with a certain slope exists. However, if we consider the flow of a granular material, we must take a couple of facts into account. This leads us directly to the disadvantages of this flow configuration if we apply it to the granular system. First, there is an ordering effect. If we consider the figure on the right, we see that due to geometrical reasons, the particles arrange in a regular pattern in a relatively dense layer directly at the wall. Exactly this ordering is problematic since the local porosity in the region between the wall and the center of this first layer of particles is comparably high. This heterogeneity is unwanted in simulations of granular materials since it may manifest in very different stress states. The second disadvantage of a flat wall BC is that there is a certain slip velocity at the wall. The granular fluid does not stick to the wall, same as a liquid would, but particles roll or slide over the wall or even may not touch the wall, as shown here. This is problematic since we cannot assume a zero particle velocity directly at the wall. Last, flows near walls are often simply not of interest, but one would like to simulate the so-called bulk behavior. This is the granular material's response far from walls. All this makes flat wall BCs unattractive in granular flow applications. We now progress to a boundary condition that is quite often used, the so-called Lees-Edwards shear boundary condition. It is named after researchers that published this approach in the early 1970s in the field of molecular dynamics, which is a computational method the DEM is connected with and has originated from. The considered computational domain is only the turquoise box located here at the center, and the shear velocity profile is shown here on the very left. We now introduce so-called ghost particles, which are simple copies of the original particles in this turquoise box in adjacent boxes. These ghost particles are needed since the original particles may collide with the particles outside of this turquoise box. In case there would be no ghost particles, there would not be any collision possible outside of this box. Also note that ghost particles are shifted into a certain direction. In our case, the blue particle is shifted in the negative z direction and the white particles in the positive and in the negative direction. If you think about those shifts, you will find that we have indicated only some of the ghost particles in our sketch. For example, we could have considered a blue ghost particle in this box here at the top. We have avoided drawing all these ghost particles to be able to explain the situation in a clearer way. Now we have to think of how we can induce a shear motion in the simulated domain. The first step to do this is to add a space shift for ghost particles that are added in the z direction. This space shift is necessary since the shear motion would lead to a deformation of the whole domain that moves this bottom box to the left and the top box to the right. You will realize that the bottom box must shifted by the space shift gamma TL to the left. And the same is true, of course, for the top box. If you think about this, the space shift is needed to simply keep the distance x of the particle relative to the right box edge. Thus, there's absolutely nothing magic about this space shift. It is again to just preserve the relative position of this blue particle with respect to the right edge of this box here. The second thing to consider is that the whole domain is deformed with the shear rate gamma. Hence, we also have to consider a shear velocity shift gamma times L. Specifically, we add this velocity shift only to ghost particles that are added in the z direction, so this one here. For ghost particles added in the x and y direction, the latter direction is not shown since it is pointing into the screen. Such space and shear velocity shifts must not be applied. For these two directions, we simply copy the particle information and displace them to one of the ghost boxes. Putting all this together yields the famous Lees-Edwards boundary condition. As you can see, it is essentially a ghost particle approach that considers the shear deformation of an imaginary box here shown with the turquoise color. Now I would like to welcome you to our next section. This is an excursion to the so-called non-smooth discrete element method. Personally, I would call this method a soft sphere DEM with infinitely stiff particles. Others call it just the contact dynamics approach. You will understand soon why the latter naming fits quite well. The researchers that developed this non-smooth DEM come from France. Here, for example, I refer to the paper of Rajai and Richefeu that was published in 2009. So let us get started with non-smooth DEM. Non-smooth in this context means that we consider particles to be infinitely stiff, meaning we consider the limiting behavior of an infinitely large Young's modulus of the particles. It is already obvious that for such a situation, classical contact force laws that we have already discussed do not make any sense. Instead, one uses so-called complementarity relationships to define the contact behavior. Specifically, these relationships describe a step change of the contact forces with the normal contact velocity. This is illustrated here on the left for the normal direction, where simply the normal force makes a step change once the normal contact velocity, which in our soft sphere DEM nomenclature would be gamma n dot, and has the meaning of a relative surface velocity. Similar things apply to the tangential direction, as you can see here on the right. In principle, we apply a force that is against the direction of motion. Of course, the method can consider slip, as in the classical soft sphere variant of the DEM as well. In summary, non-smooth DEM does not necessitate a contact force model, but relies on constraints imposed by the contact dynamics. This is also the motivation behind the naming we have discussed before. We now progress and summarize the algorithm on the next 2 slides in a nutshell. First, we need to choose a so-called coarse graining time step delta t. One then formally and not numerically integrates Newton's equation of motion over this time step delta t. Thus, when assuming a simple Euler discretization scheme, we arrive at these approximate relationships, which we then reformulate in a single vector equation, here shown on the right. As you can see, we formally considered the contact forces and external forces denoted here as Fx. The latter may include, for example, gravity. This equation now must be solved given the complementarity relationships and the known velocities u superscript minus, and expressions for the external forces, of course. Of course, also the positions of the particles matter, and they are accounted for in the complementarity relationships. In summary, non-smooth DEM is an implicit method to evaluate the post-collisional contact velocity, above indicated with a superscript plus, as well as the associated contact forces. This is done in an iterative manner within each time step delta t. We now look a bit closer at the overall time stepping procedure. First, we again stress that at the start time t, the velocities and rotation rates of the particles are indicated with a superscript minus. They are often called the left limit velocities to indicate that they are at the initial velocity the time step starts with. Second, a half step of the position x is done using this left limit velocity. Third, the contact network, including potential contact points, are identified. This is needed for the fourth step, in which the contact forces are computed from the complementarity relations. Fifth, the velocities are updated based on these contact forces and, of course, the external forces. The sixth and last step is to perform another half position update, this time by considering the new velocities vi at t plus delta t. We can now summarize our short excursion to the non-smooth DEM, starting with the advantages of this method. Specifically, this is a typically 100 times larger time step compared to the time increments delta t DEM that are needed in the classical soft sphere DEM. Also, the scheme is formally unconditionally stable. In contrast, this is not the case for classical soft sphere DEM because of its explicit force evaluation and time stepping. Finally, non-smooth DEM considers infinitely stiff particles, and hence there is no stiffness effect on the simulation results. Of course, this is only an advantage over soft sphere DEM in case the particles to be simulated are very, very stiff. However, there are also a number of disadvantages. This is, first and foremost, the significant computational effort required for the iterations in each time step. We will see later that these computations are generally really expensive and alleviate the advantages of using a much larger time step. Second, because of the infinitely stiff particles, simulations with a predefined strain or motion are challenging. The problem is that forces may diverge since, again, particles are assumed to be infinitely stiff. This results in typically huge stress fluctuations in the predictions when using such a non-smooth DEM. Exactly this is what we will show later. This is it. Our excursion to non-smooth DEM has come to an end for now, and we will consider it later in the benchmark simulations.